Hey, welcome to Dakari's 10th virtual fire investigation training session. The Dane County Arson Response Initiative is based in Madison, Wisconsin. We're a group of fire service individuals as well as law enforcement that conduct origin and cause investigations in Wisconsin. We've been around since 1997. In April of 2020, we took our training virtual, provided it to our local members for the first couple of sessions, and realized that it could be extremely beneficial to anyone in the fire investigative community. And we've now gone virtual and made it available to anyone that's interested in fire investigations. We are able to provide these to you free of charge because we are sponsored by the Dane County Fire Chiefs Association, which is a 28 member group located in Dane County, Wisconsin, and they are our primary financial resource. And we appreciate them for their continued support and allowing us to provide these trainings. Today, we have Jeremy Neagle, and Jeremy is an electrical engineer with the ATF at the Fire Research Laboratory located in Maryland. And today we're going to talk about corrugated stainless steel tubing, also known as CSST. Jeremy, go ahead and take it away.
All right, thanks, Bill. As you said, my name is Jeremy Neagle, and I'm an electrical engineer with ATF's Fire Research Lab out of Beltsville, Maryland. And we're going to talk today about corrugated stainless steel tubing. So the objectives for the training, give you a little familiarization with the various CSST products that are out there on the market. Also try to give you an understanding of some of the failure modes associated with these CSST products and take a look at some of the examinations that we may conduct post-incident, looking at these different bits and pieces. And then we'll take a look at some of the remedies if you've got CSST in a building and maybe you want to improve its safety a little bit, some things we can do to make that a little bit safer. And we'll move on through some other things throughout the session. So in detail, the things we're going to cover, go through some CSST basics. What is it? Where did it come from? How do we install it in our buildings? Then we'll look at failure modes and examinations, and our failures really kind of get broken down to two things: mechanical damage and electrical damage. And then we'll take a look at the remedies that I talked about. We'll look at direct bonding and lightning protection systems and some other CSST products out there that may have a little better arc resistance. And then we'll wind up with some legal aspects. Can't have a CSST discussion without talking about some of the legal drama that's gone on this topic. So we'll talk about some of the more relevant things there. So let's jump right in, take a look at what we've got here. So we've been using gas as an energy source since the 1800s. Back then it was primarily manufactured gas from the gasification of wood and coal in gasification plants like you see here on the right. And in the early days it was used primarily for lighting, for street lighting and for lighting in our homes. And eventually that moved to expand into heating and cooking. Over time, we've used a number of different materials for plumbing our gas systems into buildings. So I've got a list here. We'll kind of run through these, and this is typically what's permitted by most codes for plumbing our gas systems, whether it be natural gas or propane. Starting at the top, we've got steel, stainless steel, and wrought iron. These are probably some of the more common things we see. I really don't see stainless steel all that often, but certainly steel and iron. The newer installations were probably dealing with something like black steel pipe, whereas the older installations may have been wrought iron pipe. Although a lot of times these days you do hear it referred to as black iron. Most often the new stuff is black steel. In some jurisdictions, you may see galvanized steel pipe being used where there's a higher corrosion rate, maybe if you're near the ocean or something like that. And in other areas, galvanized pipe may actually be prohibited because of reactions between the galvanized coating and the gas itself. Then we're going to take a look at copper. We've got type L and type K copper. Generally, copper is only permitted if we can prove that there's no hydrogen sulfide in the gas. And with natural gas, that's always a possibility. So it's not as common to see copper used in natural gas systems. But certainly it's probably one of the primary things we see used these days with LP or propane systems. And that can be either coated or non-coated copper. And often what I see is a plastic coated flexible copper tube that's used to run propane from the tank to a house and then possibly even throughout the house. We've also got aluminum in there, not one that I see used all that often, followed by yellow brass. Yellow brass we don't generally see as piping, obviously. It would be very costly to run brass pipe, but we certainly see a lot of fittings, especially when we're looking at the flared tube fittings on copper tube, as well as the fittings we're going to talk about today on CSST. A lot of brass is being used there. Next, we've got plastic, and this is seems a little strange to be running gas in plastic tubing and plastic piping, but it is very popular, especially with utility companies. The gas company uses a lot of this almost exclusively these days for certain parts of their system. If you've got natural gas coming to your house, there's a good chance it comes in like a 1-inch polyethylene pipe right to your house. There are a lot of advantages for the utility company with this. Installation is probably a little bit easier. It comes in very long runs on spools. If they need to go longer, they can heat fuse the end of one piece to another piece and extend their run almost indefinitely as long as they can support it. Two main materials that we're looking at there, polyethylene and polyamide or nylon, are the two big ones that we see. Another big advantage with this is for the utility companies, they can get away with installing less valves. So in a traditional system with rigid piping, metal piping, they would probably have to install a lot of service valves and things like that and valves in their system to shut off or isolate certain portions for maintenance and things like that. With plastic pipe, they can get away from using all those valves. And basically what they do is if they have an issue or they need to isolate a certain service, they can dig up a section of the tubing, apply a clamp to it, pinch off the gas flow, complete their downstream repairs. And when they're done, they release the clamp, the pipe returns back to its original size and shape, and they're good to go. They don't need to worry about actually having a separate valve at that point. So that offers a big advantage to them, probably both installation and maintenance costs. Then we're going to move into corrugated stainless steel tubing, or CSST, and obviously that's what we're here to talk about today and what we're going to focus on for most of this session. It comes in two basic varieties, yellow and black, and we'll look at both of those. Then we're going to move into flexible gas appliance connectors. We're going to talk about those as well because they kind of fall in with our CSST a little bit. They're a similar construction, but a very different product. And then we've got a couple things that are not permitted. So basically what's not permitted are materials that are going to be very brittle, that are going to crack or fracture easily. Things like cast iron or PVC or CPVC plastics. Obviously, we don't want to run those in our buildings containing a pressurized flammable gas. So moving into the CSST, what is it? What is this stuff that we're talking about? Pretty simple. The name kind of tells the story. It's a corrugated stainless steel tubing. It's flexible, and it's used to distribute fuel gas, whether that be natural gas or propane, through residential, commercial, and industrial structures. And it gets used quite widely in all of those. We see it a lot in residential, but certainly it has applications in commercial, industrial situations as well. Got a few images here on the screen, and this is it. This is what we're talking about. So three different products that we have here. On the left, our yellow product is what I'm going to call our legacy or our original CSST product. Back when the product first hit the market, that's what we were dealing with. And if we look at the construction, it's pretty simple. We've got a thin wall, stainless steel tube, which has been corrugated. The corrugations give it some strength and rigidity, but allow it to remain flexible. And we've jacketed that in a yellow plastic jacket material. And in that original design, that yellow jacket really served no purpose other than to smooth out the corrugations to make it easier to pull that stuff during installation. If you're pulling it through, holes in a framing member or something like that, it smooths it out so it pulls easier. On the right, we've got two black jacketed products. These are newer products that we'll talk about a little bit more in depth later on. The jacket on these does become important. So we start seeing some different things go on with the jacket during installation as far as requirements go, if there's any damage or anything like that. And again, we'll talk about those more in depth. So that's effectively what CSST is. And this is what CSST is not. And this is a common mistake or common misconception that I see. People see these things and they think, hey, I've got CSST in my building. Well, no, what you've got is a flexible gas appliance connector. It looks very similar. Its construction is similar, and it's easy to understand why people get confused by this. What Well, they're both yellow. They do come in other colors. I've seen yellow, black. I've seen raw stainless steel with no coating on it. It's corrugated. It looks very similar. It's flexible. It's made of stainless steel. The older ones were brass. The modern ones are all stainless steel. So by nature, it is a corrugated stainless steel tube, but it is not CSST as the product as we know it. These are built to different product standards. The gas appliance connector is ANSI Z21.24 versus ANSI LC1 for CSST. And if we look at them, we can see that they're similar but different for sure. The gas appliance connector is corrugated. We can see the corrugations versus the CSST. We obviously see that plastic jacket has smoothed a lot of that out. The coating on the gas connector is typically an epoxy or paint type coating, whereas we've got this thicker plastic jacket on the CSST. The corrugations on the gas connector are helical. They kind of spiral along the tube, whereas the CSST uses an annular ring, just a series of rings stacked next to each other. The big thing is really the connectors on the end of the flexible gas appliance connector are factory installed, whereas with CSST, we're applying those in the field as part of the installation. You cut the tubing where you want, you add a connector on there to manufacture the whole system or to assemble the whole system. Flexible gas appliance connectors come shipped as a complete product. They range in size from 1/4 inch diameter up to 1 inch diameter and have a maximum length of 6 feet. So these are short comparatively. You can have hundreds of feet of CSST run through a building, but our flexible gas appliance connectors are really limited to a specific application where the system extends from the building's fixed gas piping to a movable appliance or an appliance that may vibrate and needs to isolate the fixed gas piping from that. So these are really meant to be that intermediate step right at the end of the gas system extending to an appliance. So let's take a look at where CSST came from. We've been plumbing gas into our building for, well over 100 years, and we've used things like iron pipe and steel pipe to do it, a lot of rigid piping systems. And that's worked out very well for us until you get to places that have a high rate of seismic activity, a lot of earthquakes. So west coast of the US, we get out to California, they have a lot of earthquakes out there. Obviously having a rigid piping system in your building, which may crack during an earthquake, it gives potential for leaks, which could then turn into fires or explosions. So something needs to be done about that. And in California, they took one approach, and that was to design or come up with a seismic valve, which would typically be installed at the service entrance of a building. That valve is going to sense movement of the building during an earthquake and shut the valve, closing off the flow of gas going into the building. So if the piping cracked, you have no more gas flow. It really wouldn't matter. So that kept things safe in that situation. In Japan, they also have a high rate of seismic activity, a lot of earthquakes, and they took a different approach. They looked at it and said, well, I've got a building that's moving and swaying during an earthquake. I need to have a gas system that can move and sway along with the building without causing damage. So they came up with this corrugated tubing system that we now call CSST, and that's really how it was designed and where it came from. It came into the US in the late 80s, and we've been using it ever since, and it's really grown in popularity, definitely a lot in the last decade or so. But it's been around for a while, and we have been using it for a while, and some good and some bad. We've seen some issues, but obviously there's a lot of advantages to it. So it's very attractive to installers and builders. It provides a low-cost method of installing piping into the building. If you imagine what it takes to install rigid steel piping, you need to have a fair amount of machinery and equipment to cut the pipe, thread the pipe, get all the parts assembled. You need to have some training and knowledge how to do that. Whereas CSST comes on a roll, you roll out as much as you want. You can use basic hand tools to cut it, basic hand tools to apply the fittings. It doesn't really require a lot of extra equipment to get this stuff where it needs to be. It's well suited for retrofit applications. If you've got an existing home, it would be very difficult to run 10 or 20 foot sticks of rigid pipe through the walls without really tearing the walls apart. Whereas with CSST, you can drill a few holes and fish it through pretty easily, bending it around where it needs to go and getting it to its final location. One of the other things that we see as an advantage is there's a potential for a reduction in the amount of fittings and joints. Again, with rigid piping, it typically comes in 10 or 21 foot lengths. Anything longer than that, you're going to have to start using union fittings or elbows or other fittings to join these pieces together. And everywhere there's a joint, there's some potential for a leak. With CSST, you can get this stuff in rolls up to about 1,500 feet. So you can run it just about as far as you could ever possibly need to. And if you need to run it further, you can put a union fitting in there and extend it to another roll. So in reality, you really could have a long run of CSST with one fitting on one end and one fitting on the other end, and really eliminate a lot of joints in between. In practicality, that probably doesn't happen as often. There's always shorter pieces that get joined into the systems. Obviously, the installers want to use all of the materials they have. So I do tend to see unions and other fittings and runs that have been extended through multiple pieces. So some of those fittings do still exist, but it is possible to have a fewer amount of them. CSST ranges in sizes from about 3/8 of an inch up to 2 inches. 3/8 of an inch would probably feed a small single appliance, maybe something like a decorative fireplace or something like that that's not producing a lot of heat. Whereas 2-inch, maybe we're looking at the feed run for a manifold that runs a number of different appliances, or maybe it's a large piece of machinery or equipment in an industrial setting. We may see those larger sizes. These numbers are a little bit old, but the manufacturers seem to indicate that about 55 million feet of CSST are sold per year, with over 1 billion feet installed since it was introduced. Again, these are a little bit old, so I expect that number is quite a bit higher at this point. There's certainly a lot of it out there. We see it in a lot of new construction, and a lot of it being used in retrofits to existing construction, whether that's adding gas to a building that never had gas in the past, or you're adding more appliances to a building that maybe had only 1 or 2 to start. Comes in 2 basic varieties, black and yellow. We'll talk about both of those as we move on. We already kind of said the yellow is the original legacy product, and the black is our newer product, what we're going to call arc resistant or lightning resistant CSST. And we'll look at the difference in those a little bit later on. Looking at our photos here, we can see a couple different things. So on the left, we've got a pretty sizable gas installation. No matter what kind of piping you're using, that's a lot of gas in a building. But certainly for CSST, that is a ton of CSST there. On the right, we've got what's probably pretty typical in a lot of the multi-story apartment buildings that we're seeing coming up around the country these days. Maybe you've got a number of apartments, and each one has 3 or 4 different gas appliances in it. So we run a large bundle of CSST through the building and branch off a few runs to each unit as needed. A few more installations. This is another large apartment building. I think this unit had something like 400 apartments in it, multi-story. And this is actually the photo on the right, on the left is the gas meter room as it exists unfinished. So we see a lot of runs of CSST coming in there, and they're actually being pressure tested before they're terminated and connected to the gas meters. Over here on the right, we can see a bundle of CSST that's running through the building. This is actually going from one floor to the next and exiting through a hole in the floor and extending up beyond that. Eventually, this hole in the floor is going to be fire stopped, and then the entire assembly around it's going to be sheeted in drywall, and all that stuff would be hidden behind the finished walls, and you would never know it's there. When I start looking around buildings, I start to focus on things like this in the lower right, where I've got this is a fairly large piece of CSST, like maybe about 1.5 inch diameter CSST feeding something. And then we've got it crossing over a sprinkler pipe. And I've also got some electrical wiring in the same area. Those are things that get me interested, that I start looking at as potential places where I could have failures or problems in the future. So those are things that I tend to think of as being interesting. Got a number of different manufacturers that are making CSST. Some are manufacturers that were making it in the early days when it was introduced and have gotten out of the business, and some are still around today. So when I look at something like Parflex, that was a product made by Parker Hannifin. I don't believe they're producing that product anymore, but it was around in the early days when CSST was first introduced. TrueFlex is another one that was around in the early days, and I believe TrueFlex is spun off that product line, which I think is now ProFlex, if I'm correct on that. Then we've got a few other big ones that we run into a lot. Omega Flex, which makes track pipe and track pipe counter strike. Tight Flex, which makes gas tight and flash shield. There's a few others that we start. All right, I think we had a small technical issue. Hopefully we've got that resolved. I'm going to go ahead and repeat what I had on this slide, and then we'll move on. So here are some of the manufacturers that are producing CSST products, and some of these were around in the early days of CSST and maybe have gotten out of the business, and some are still producing products today. So if I look at Parflex up here in the top right, Parker Hannifin, I don't believe they're still producing that product, but you may find some out in the field. TrueFlex is another one. They used to produce a product which I think has now been spun off as ProFlex. Then there's a few other big ones that we run into. Omega Flex, which makes track pipe and counter strike. Tight Flex, which makes gas tight and flash shield. Ward Flex is the flexible product for Ward Manufacturing, which makes a lot of steel pipe and steel pipe fittings. This is their flexible line. And then there's a few newer ones that we start to see popping in, like Home Flex is one of the brands that we see at some of the big box stores out there. So there's some newer manufacturers that got into the business a little bit later on. So now we've got a product which has come in from Japan. We want to start using that in our installations. So the first thing we need to do is put together a product standard that we can test and certify this stuff to. And around 1987, a group gets together and puts together this document, which eventually ends up being adopted as ANSI LC1, which is the standard for fuel gas piping systems using corrugated stainless steel tubing. And this is still the document that we're using today to design, test, and certify our CSST products that we have out there on the market. So now we've got a product standard, we can certify this stuff. Now we need to get it into our installation codes so it can be installed and accepted by local jurisdictions. And that's something that's controlled by the National Fuel Gas Code, NFPA 54. In 1988, CSST was first introduced into NFPA 54, and it continues to be in there through the current edition. So with some of our older piping systems, steel pipe and the like, it was pretty straightforward on how these things would go together. And installers were trained typically through the apprenticeship process. Plumbers and gas fitters would be trained on how to cut pipe, thread pipe, and assemble it to make gas tight joints and things like that. And it's pretty straightforward. As long as you're making your threads properly, they're all NPT threads. They all fit together nicely. So I can buy pipe from one manufacturer with threads on it, or I can thread the ends myself. Then I can buy fittings from another manufacturer, and they're all going to fit together. It doesn't matter who manufactured which piece. CSST is a little bit different. It doesn't quite work like that. It's a system. The system consists of the tubing, the fittings, and all the bits and pieces that go along with it that the manufacturer may make and sell. And unfortunately, there was enough flexibility left in the product standard that gave the manufacturers some ability to meet the goals, meet the requirements in different ways. So if we start to look at how these things are manufactured, one manufacturer's design is going to differ quite a bit from another one. So if we look here at the photos or images that are on the screen, on the top left, we've got this black jacketed product and its associated fitting. And we can see on the inside, there's a pretty elaborate ferrule system that crimps down on the piping, as well as on the aluminum in the jacketing material to make sure that we've got a good connection and a good seal. On the right, we can see this one here uses a nut backed up by a split ring, which gets compressed over the tube to make that joint. And down here on the bottom right, we've got a couple of them that are using a couple of washers, different size washers, and a rubber O-ring. So 3 different manufacturers, 3 different designs, they all accomplish the same thing, but they've all done it a little bit different. So I can't go out and buy Ward Flex tubing and use a track pipe fitting on it. I've got to make sure I stick with the same manufacturer all the way through with all the bits and pieces. And each manufacturer is going to have a catalog full of parts, all the different fittings and tubing and accessories that they make and provide to go along with those systems. And there are going to be things like hardened steel striker plates and protective conduits, maybe cast or fabricated manifolds, lots of different fittings for stub outs or flanges, unions, different fittings with different threads on the end, whatever the case may be. If there's a need, they've probably got a piece or a part that fills that need. And again, the real critical part is making sure we've got continuity of manufacturer through all of these, that you're using the same manufacturer for each bit and piece of the system. Some typical installations of what CSST may look like. This is actually a residential installation. It's maybe a little more involved than some. This is actually a 2 PSI propane system. So we see a couple extra things that we might not normally have. Right down the middle, what we see is a larger diameter piece of CSST comes in from the top and then branches off, goes through a couple of pressure regulators to get our pressure down to the pressures that we need, and then runs out to various different appliances in the home through a couple of manifolds. And that's pretty typical. You may not have those extra pressure regulators in some systems. You may have a larger manifold or a smaller manifold, depending on the number of appliances we're dealing with. But that's typically how it's done. Most of these tend to be built off of a manifold system with a home run from each appliance back to the manifold versus a traditional system using, say, iron pipe or steel pipe, where you'd have a main run through the house and then branches coming off of that going to each appliance. A couple more installations we can see here. This one on the right, we've got steel pipe coming in and then a steel manifold, and that manifold is made from iron or steel pipe tees and pipe nipples. So they've fabricated that on site. And then we run out to multiple appliances. Over to the left, we can see a purchased or prefabricated that looks like a cast manifold there, and then running out from that as well. So again, just differences in how the installer decided to do it. I'm sure there's a difference in cost in purchasing a manifold versus building one out of plumbing parts that you may have on hand. CSST is intended to be installed by qualified, trained installers. That's definitely true. It's different enough from screwing together pipe thread that they started to realize that we need to have some good training, and the people that are doing this really need to know what they're doing and how each system works. It's really not meant to be installed by the do-it-yourselfer. That wasn't the intent. Unfortunately, that's not really how it's shaken out. So I can go down the street right now to pretty much any major hardware store or big box store and find this stuff on the shelves available for purchase. Here's a couple of big ones. I'm not picking on these guys by any means. Most larger hardware stores and big box home improvement stores seem to be carrying some amount of CSST at this point, and that's pretty universal around the country. I mentioned that this was meant to be installed by trained, qualified installers. And when they wrote the standards, they realized that this was different enough from most other plumbing products that they needed to build something in to address that. So it's actually required that you have factory training to purchase and install this stuff. And you would get a qualified installer card from each particular manufacturer that you wanted to install that says that you've been trained and you're qualified. And then that would allow you to purchase it. And ultimately on the back end, an inspector or AHJ could ask to see who installed it and make sure that they have this card to show that they were properly trained and qualified. We first ran into this at the lab a number of years back. We had a case that involved some CSST, and we were going to do some testing. So we called down to our local plumbing supplier and said, hey, we need a couple rolls of CSST and a whole bunch of fittings. And they said, okay, we just need to see your qualified installer card. And we said, or what? No idea what they were talking about. And they said, you need to have a card that says that you're qualified to install this stuff so we can sell it to you. And we said, no, you don't understand. We're the federal government and we're running this test and it's very important and we need to have these materials. They said, that's great, as soon as you show us your installer card. And they would not sell it to us without having that card. So they put together training for us. We went down, sent about a dozen people and sat in their facility and had a manufacturer's rep train us on how to cut the tubing and prepare the ends and apply the fittings and all the different bits and pieces and how to design the systems. And we all walked away with a nice little installer card that said that we had been factory trained. And that's great. That's really how the system's meant to work. There's checks and balances. And I think that was probably how the system was envisioned. Unfortunately, it hasn't always come out that way. So I said you can go down to the local box store and pick this stuff up off the shelf. And that's something that I've certainly done before. And I've walked in, loaded in a cart, paid for it, walked out, no questions asked. I did have one instance where I walked up to the register with a cart full of CSST products. And as the cashier scanned the roll of CSST, the computer dinged and he kind of looked at it for a minute, puzzled. And it was raising a flag and telling him that he needed to ask for a qualified installer card. And he says, qualified installer card? Like, very confused, didn't know what it was asking him for. And I said, yeah, you're supposed to be factory trained and have a card that says that you're qualified to install this stuff. And he says, oh, okay. Continues on scanning the rest of the products, and out I went, never showed a card. So unfortunately, the follow through is not real good. And what's happened is each manufacturer has a little booklet that they call their design and installation guide, and that specifies all the requirements to install their product and how to make the fittings up, how to prepare the tubing, how to cut the tubing, things like that, how to size and design the systems. And when you go to your big box store, they're going to have a shelf with a bunch of products on it, CSST products, and on the end of that shelf will be this little booklet. If I buy that booklet, read it, and go to the back page or the back cover, on that back page is going to be my qualified installer card. I fill in my name, and now I'm good to go. I've read their material, and they've given me a card with a number on it that allows me to say that I've been qualified as an installer. Going a step further, most of the manufacturers now have realized that they can put their training materials online, either on their website or on YouTube. I can go on their website, view the materials, check a box that says that I viewed them, download and print my own installer card. So I'm good to go now. I've been factory trained. I don't think that's what was envisioned originally, but that seems to be how it's working out. Unfortunately, it leaves a lot of ability for people that haven't actually read or viewed the materials to be out there installing the stuff, purchasing it and installing it, that maybe don't have the level of training that was really needed to put this stuff together safely or to safely size and design a system. So I've mentioned a couple times sizing and designing the system, and that really is something that's covered in the design and installation guide. It's going to go through some basic math, some calculations and some tables to tell you, based on what size appliance loads you have, how big of a tube you need to use to get the right amount of gas there without affecting downstream pressures, which could then obviously affect performance of the gas appliance. It may cause it to burn improperly or ineffectively. And those are things that if you've been properly trained, you're going to understand, you're going to know, and you're going to know where to look for that information. If you just went and bought this stuff off the shelf, maybe you don't have that knowledge. So it leaves the potential for undersized systems to be out there where there's too much restriction in the gas tubing up to the appliance. And now maybe we're getting reduced pressures going into our appliance, which can result in improper combustion, high levels of soot production, high levels of CO production, and things like that, which can cause some other problems with our appliances and how they operate. So let's talk a little bit about installing the CSST, where we can install this stuff and how it gets rooted and run and installed. Really have a lot of options there. I can run it through walls, I can run it through floors, ceilings, exposed or concealed. So if I run it through a wall, it's probably going to be concealed behind drywall. I don't have to worry about the fittings. They're allowed to be concealed. Being an electrical guy, I'm used to having splices and connections for electrical wiring accessible for inspection later on. And we don't seem to do that here with CSST. It's perfectly acceptable to bury the unions and the joints and the fittings back behind the wall where you're never going to see them again. In an attic space or a basement, you may run them exposed where they're just supported by the framing members or other things that happen to be there. So we could really have it either way. Generally, CSST shouldn't be used outdoors unless it's specifically been approved for that. And it seems now that most CSST products I've seen are rated for UV exposure and outdoor use. I think some of the earlier ones were not. In this lower picture, we can actually see the jacketing. That was yellow CSST, and you can see the jacket is all discolored and cracked, and portions of it are falling away from the tubing. Obviously, that's probably one that was not suitable for outdoor use and is having some issues with that. The one up here above, we can see we've got a nice tight bend, which is probably not in accordance with the minimum bend radius requirements. We've got some mechanical damage to it. So it's been installed in an area where something can impact it or abrade it, and that could potentially cause a leak later on. This one down here again, you can see that that bend is probably a little bit too tight. These things do have a minimum bend radius that needs to be followed, and that's another one of those things that's specified in the design and installation guide. It's going to give you, depending on the size of your tube, it's going to usually be a multiplier of so many times the radius of the tubing is the radius of your bend that you're allowed to put in that stuff before you start running the risk of damaging the tubing or kinking it. And we can see in this picture on the bottom left, that one probably had a twist in the tubing, and as they were pulling it through the building, yanked a little bit too hard and actually pulled a kink into it. And really at that point, there's no way to get that out. If you try to work the kink out of it, now you're probably going to be doing more damage and potentially weakening and even cracking the tubing and could possibly cause a leak in doing that. Generally, CSST is not suitable for direct burial or encasement in concrete unless it's properly protected. And properly protected generally means installed in a vented conduit. So if the installer has to go through the process of installing a vented conduit, which is basically a pipe, to run their CSST, they're probably just going to run the pipe and forget the CSST altogether. I really haven't seen too many of those installations, other than maybe where a piece passes through a masonry wall or something like that and they have a short piece of pipe to protect it. There is a product out there which is somewhat new. It's the product over here on the right, which has its own integral vented conduit. So the black jacket on it is a very thick, heavy-duty black jacket that gives it some mechanical protection or physical protection while it's buried or encased in concrete. And if we look right here in the center picture, see that little blue piece on that fitting at the end? That's actually a vent. There's a little blue plug in there and a vent that can be opened up to allow us to vent off any gas that may have leaked inside of that black protective conduit. It's out there, it's on the market. I've never actually seen it in the field. I gotta imagine it's pretty costly, and I just don't think installers have really fully embraced it and started moving to using that in their installations. So I can run CSST just about anywhere in the floors, walls, and ceiling. How am I going to support it is the next question. And again, being an electrical guy, I'm used to supporting my electrical wiring at regular intervals by very specific things. With CSST, the codes and installation rules are pretty broad on that. I can use just about anything. And the things that I commonly see are things like these metal or plastic J hooks, metal or plastic clips with either one fastener or two are common. If you're on a roof, say, for example, you've got a rooftop HVAC unit that's got some gas connections to it, you can run the CSST up there, assuming it's rated for the outdoor use. And they make these roof blocks that you can use to support it up on the roof. One of my probably least favorites is suspended ceilings. If I have a long run of CSST to get from one side of a room to another, and I've got a suspended ceiling, I can take the CSST, run it up to the void space above that room, and just string it right over the top of the suspended ceiling. It doesn't need to be secured other than laying on top of the ceiling tiles and ceiling grid. The concern I have with that is anywhere I have CSST running in proximity to other conductive components, any other metal parts, whether it be that ceiling grid, lighting fixtures that are installed in the ceiling, or something like that, I have more potential to have issues with lightning damage, and we'll talk about that a little bit more as we go on. Structural framing members are another big one. Whether I'm drilling holes and running horizontally through wall studs, or suspending it from framing members in a basement, or just laying it on top of the bottom chord of a truss in an attic space. Those are all perfectly acceptable for supporting my CSST. And then the last one is other utilities. So I can support this by looping it over other piping, metal ductwork, electrical wiring, or other utilities or other systems that may be existing in the building, which is great for supporting it. But again, if I'm dealing with other conductive materials, other metal components, I start to run the risk of having some lightning issues later on if things get energized by lightning energy. Where CSST is terminated, it needs to be done in a fashion that prevents strain on the tubing and fittings. And the manufacturers provide a wide variety of products to do that: flange fittings, pipe stub outs, all sorts of different things that you can use to secure the end of that to the structure and then transition to something like a flexible gas appliance connector to connect directly to your appliance. That way, it's not going right into the back of the slide-in range or going right into the back of the clothes dryer, which is vibrating and moving around. We've got some isolation of the CSST system from that appliance that may be moving or vibrating. In areas where the CSST is restrained, places like where it passes through framing members or comes up out of a floor and makes a sharp bend up into a wall, we need to provide some protection there. And the idea is, if I put a nail through that wall to hang a picture or something like that, if I'm just in the middle of the wall and the CSST is free floating in that void space, it should be able to move out of the way of the nail. When the nail hits it, it should just push it aside without puncturing the tubing itself. Again, we usually don't really care about the jacket. We're more concerned about the tubing itself, which is actually containing the gas. So we start to require things like steel striker plates. In the center photo, you can see a bunch of individual steel striker plates where the CSST is running through the top plate of a wall, it looks like here. And then we've got a large steel striker plate down a little bit lower, protecting it in that area. Got a couple of pictures that basically show that. On the right, we see an example where our CSST is coming through a floor and then transitioning up into a wall. That's another common place. Maybe it's a stub out for a gas range or something like that, where we make that sharp bend and come up into the wall. The CSST really can't move very well in that area. So we need to put something in there to protect it. And the steel striker plates may not be the best option. So we start to see these things that are generally referred to as floppy conduit. And we can see a couple photos here. So on the right, we've got a stub out for an appliance. And just above that, on our CSST, you can see that that silver sleeve is a interlocked metal tape, helical wrap type. It's just a flexible conduit that provides some mechanical protection to it. Over here on the left, you can actually see we've got a striker plate at the top and then some conduit down below that to provide some protection for that bit. So let's take a look at some of the failure modes associated with CSST and some of the things that we might look at during examinations. So failure for CSST really comes down to two different things: mechanical damage and electrical damage. And electrical we can break down into electrical damage from the building electrical system or from lightning. Those are the two big ones we look at. Regardless of which type of damage we're talking about, it really comes back to the same root cause. And it's the wall thickness of the CSST. So if we start looking at the wall thickness on copper tube or steel or iron pipe and things like that, that we permit, other ways that we permit installation of our gas systems, they're all pretty robust, pretty thick walls, pretty heavy duty, and tend to just by their nature do pretty well with mechanical damage as well as electrical damage. When we look at CSST and we saw that cross section of it, it's a fairly thin wall tube. It really gets a lot of its strength from the corrugations, but from punctures and arc damage, it's just the mass of the metal that's really affecting that. So CSST, we're typically looking at 0.008 to 0.01 inch wall thickness, which is not a lot of metal, especially when we can compare it to those other products. And we do start to see issues with nail punctures or screw punctures if this stuff is in an area where we can hit it and it's restrained enough to allow the nail to go into it. And then again, arcing from the electrical system, that's something that we'll talk about a little bit. And then lightning damage is probably one of the bigger ones that we deal with when we're talking about CSST. So as far as arcing from the building's electrical system goes, we've got a corrugated steel tube, which is coated with a fairly thick non-metallic jacket, plastic jacket. So in order to get any arcing in there, we're going to need to fail that jacket or get through that jacket in some way. On the other hand, our electrical wiring should all be insulated as well. In a residential application, we're probably looking at something like non-metallic sheathed wiring, Romex, which is going to have insulation on the conductors and then an outer sheath or outer jacket as well. So we've got to get through those layers of plastic. And where we see this happen a lot is during fires. So we may come in after a fire and start looking around at things, and somebody may say, hey, there's a hole in this piece of CSST. Maybe this is a CSST fire. And after a closer look, we start to realize that, well, during the fire, we're burning the CSST. Maybe we burned away the jacket. Maybe we burned away the insulation on the wiring. and maybe that wiring was in contact with the metal tube, and we had a direct short circuit, and it allowed it to arc and form that damage in the CSST. In that scenario, the fire was pre-existing, so it's not a CSST fire. The CSST then maybe makes the fire gas fed at that point and changes the, how the fire burns in the building, but the original cause of the fire is still something else. So that's something that we have to consider. Of course, there are ways that the wiring can short to the gas tubing independent of fire, but those are probably a lot less frequent because we're dealing with multiple layers of plastic. You'd have to have a lot of mechanical damage or abrasion or something like that to allow that to happen, or an improper installation where too much of that material was stripped away during the installation process. Going to take a look at a quick video. This is a video I made in the lab arcing a piece of non-metallic sheath cable to a piece of 1/2-inch CSST. So let me bring that up for you real quick. So what I've got is a length of 1/2-inch CSST. I've stripped away a little bit of the jacket material, and I've got a piece of number 12 Romex wiring, again, stripped away a little bit of insulation. I'm going to give it a little nudge to cause that short circuit. We'll see a quick flash followed by a small gas-fed fire right at that location in the center. And there it is. We've got a small flame. It's not gigantic. We're dealing with natural gas at 1/4 psi, which is a typical system pressure, about 7-inch water column. And you can see we're burning right there on the surface, mostly burning gas at this point. I'm going to speed this up a little bit. We'll go a little bit further in. And let's see, right about here. So at this point, I've turned off the gas supply, and you'll see the gas flame kind of dies down. And what's burning from this point forward is the jacket material. And you can see it burns pretty regularly, pretty freely. It'll continue to propagate along the tubing. And as it's burning, we're dripping flaming drops, which could then extend to other combustibles. I'm going to stop it real quick right here. And you'll see that we've burned away, a fair amount of that jacketing off of the CSST, and it will continue to progress toward the left as it moves along. One thing you'll notice is not burning is the insulation system on the wiring, and there's a reason for that. With electrical wiring materials, the insulation and plastic materials that we use for insulation are designed not to support combustion. They're designed to self-extinguish after the heat source has been taken away, and that's what's happened here. So we've extinguished the gas flame that was right there at that point. The wire insulation self-extinguishes, but the CSST insulation or jacket material does not. It continues to burn. Jump back over to our presentation. This is another test that was conducted by one of the engineers out of our lab. This is actually in an acquired structure. I believe this is propane, probably about a 1/2 psi, around 14-inch water column. And same thing, he's got a run of CSST that they've installed in the attic space of this structure and a run of wiring. You can see they've stripped away some of the wire's insulation, and they're basically going to do the same thing and let it progress beyond that point. So this is after the arc has occurred. It's ignited the gas. You can see we've got a pretty good gas jet or jet of fire extending from that CSST, which is now impacting our structural members, right? So we've certainly got enough fire there to get our surrounding combustibles involved, which is what happens in this case. Obviously, they've conducted some live fire training in this structure, and this is what's left over afterwards. You can see all the framing is now a bit charred, and we've burned away all of the jacket material on the CSST and all the insulation on our wiring. So we're just left with the bare components. And there's a couple of wire ties here. One is applied right here, and that's signifying where the hole is in the CSST. And there's another one back here on a piece of the wire, piece of the conductor, and that's signifying where the arc damage is on the conductor. So we've got mating damage on those two surfaces, indicating where that arc had occurred. And if we zoom in on the CSST, you can see the hole. And it's not real big. That's it right there, that little dark spot. That was producing probably about a 12 or 14-inch flame jet, which was extending out of there. Again, we're dealing with propane at about a 1/2 psi. So it's not a lot of gas we're supplying to this, but we're getting a pretty substantial flame coming out of that small hole, which is obviously enough to get the surrounding combustibles involved. So there have been numerous incidents around the country and even outside the US documenting lightning-induced damage to CSST systems. If you Google CSST and lightning, it will return a wide variety of results. You will get a lot of case studies, a lot of news stories, a lot of research reports, a lot of other information relevant to those topics. It's pretty well documented at this point. There's a lot of papers out there from both sides of it. There are definitely different views, some indicating that there are issues with CSST and others explaining how safe the product is. So read those and take them for what they are. But essentially, here's what we've got. You look at this scenario in the top right, we've got a run of CSST. This looks like it's a basement. And we've got a couple of HVAC lines running through there. And we've had some arcing between the HVAC lines, it's probably a copper line, and the CSST. We've had a little flame jet extending up from there. And that's extended to some of the combustibles that were surrounding it in the structure. It's been pretty well documented in a lot of these cases that lightning can perforate the CSST, it can punch a hole in it, and at the same time, it can ignite the gas. And that's a pretty important thing to know, that we don't need a separate ignition source. So once this fault occurs, we may have a failure or fault that allows gas to escape, and it may ignite the gas at the same time. So we've perforated it, we've got a leak. If the gas ignites, pretty obvious we get a fire, assuming we have other. So it's been pretty well documented that lightning energy can perforate the CSST tubing. And at the same time, not only are we creating a leak, we can ignite the escaping gas, which is a pretty important thing to keep in mind. It doesn't require a separate ignition source. The event that caused the hole can also cause ignition of the gas if we've got the right conditions. So if we have a hole in the CSST, we perforated it, we've got gas leaking out. If that gas gets ignited in the process, we can have a fire. I think that's pretty straightforward. And if that fire is in close proximity to other fuels, that obviously can spread throughout the structure. If the gas doesn't ignite immediately, or it ignites and then goes out, we now have the risk of raw fuel gas venting into confined spaces or concealed spaces or attic spaces or basements in the structure. And that, if allowed to build up over time, could present a risk of an explosion if it finds an ignition source and gets within the flammable range. The picture here on the screen is actually the remnants of a fairly large log home down in Texas. They knew they had a lightning strike sometime in the past. They had CSST in the house. They had it inspected afterwards. They found some leaks. Somebody came out, made some repairs. They thought they were good to go, but unfortunately they did not fix all the leaks in the system. And a time later on, when the gas was restored, they had a leak, ultimately had an explosion, which pretty much leveled this house and unfortunately killed one of the occupants. So that definitely can happen, where we've got gas leaking out in a space where that piping exists, and eventually building up to a flammable level and finding an ignition source. So I've got another video we'll take a quick look at here. This is me playing around in the laboratory with a piece of CSST with various size holes in it to get a better understanding of what the flame's going to look like coming out of these holes at various sizes, and how that's going to look, and that, what that's really going to look like on a scene. So let me bring that video up for you. A half-inch piece of CSST. Let's stop it real quick here. A half-inch piece of CSST, and everywhere there's one of those pieces of black tape on there, that's a piece of tape covering up a hole, and the holes range from about a 0.5 millimeter diameter up to 5 millimeters. So this first one we're going to look at is a 1 millimeter diameter hole, which is probably on par with the other images we saw from the other tests, roughly about the same size hole. I've got natural gas connected to this, running at about 1/4 psi, which is a fairly typical system pressure. I'm going to go ahead and ignite that with a lighter, and we'll see what that looks like. So probably about a 10 or 12-inch flame coming out of there. And one thing you'll notice is every time I remove the flame, the pilot flame from the lighter, and move it away from that gas jet, it self-extinguishes. The gas coming out of that hole, the velocity is too high and it kind of blows itself out. So that's certainly a possibility. If we get a small hole and the gas doesn't ignite right away or does ignite briefly, it may blow itself out. One thing to consider is if I have an obstruction, which is a reasonable thing to consider here. If I've arced to the CSST, it arced from something or arced to something. It may be another pipe, it may be a wire, it may be structural steel, it may be something else, but there's probably something close enough to consider it as an obstruction that gas jet may impact, and it may slow down the velocity of the gas and help the gas and air mix to the point where we then get sustained combustion. So I'm going to place in front of the hole, it's not in direct contact, but just above the piping, it's just about a 1/2-inch metal rod. I'm going to place that in there. The gas jet's going to hit that. It's going to allow it to self-sustain at that point. So once I light it, now I've got sustained flaming there. Let's see that one more time. And that flame will stay there as long as we have gas supplied to the system and the geometry between the obstructions don't change. Going to go ahead and jump forward a little bit. And we'll take a look at a larger hole. So this is going to be a 3mm diameter hole. So a little bit bigger than the last one we talked about, but still fairly small. Same gas, same pressure, natural gas, about 1/4 psi. And I'm going to light that one. And what you'll notice here is that that flame sustains. It does not self-extinguish. It doesn't blow itself out. It's kind of hanging there in free air. It's lifted away from the CSST a little bit because we haven't mixed the air and the gas at that point. But it tends to burn, above that a bit in free air. And again, it'll burn there consistently until we remove the gas supply to that. So depending on the size hole that we get and whether or not we have an obstruction has a factor in determining whether or not the flame is going to sustain or if it's going to blow itself out. So let's talk a little bit about lightning and CSST. This image here is actually an image of some testing that was done on one of the black jacketed CSST products. We can actually see that right here laying across the table in the test. And then we've got a wire coming out above it that's discharging a high voltage, high current electrical energy. And we can actually see that energy being dissipated and traveling over the surface of the jacket of that CSST product. When we start talking about lightning, we've got two basic different types of strikes we can have, a direct strike and an indirect strike. And a direct strike is pretty straightforward. It's when lightning strikes your building. So lightning has struck the house, it hit the chimney, it hit whatever. But it's all the lightning energy going right into your building. And those things are very difficult to deal with. It's very high energy. And just about any system in the house is going to have a hard time dealing with that. There's a good chance you're going to have a fire or some sort of incident just based on the amount of energy that's been funneled through that building or that structure. And we kind of recognize that. So those kind of get written off that we're probably not going to be able to deal with those very well. If it happens, you're probably going to have an incident. The indirect strike, where maybe it strikes a nearby tree or some energy from a nearby lightning strike gets funneled in through electrical lines or gas lines or cable TV or something like that. Those are the types of strikes that they're lower energy. We can deal with those a little bit easier, and we can try to design our systems and our components to handle that a little bit better. And those are the types of things that we're mainly dealing with when we're talking about lightning strikes. If we look at lightning throughout the country, this is a cloud-to-ground flash density map of the U.S. For about 10 years. We look out on the West Coast, a lot less lightning out there. Of course, they've got earthquakes and other things to deal with, but their lightning problem is certainly not the same as Florida and Texas and a lot of the Southeast. But really, a lot of the country has enough lightning for it to be a concern. And that's kind of what I wanted to get across from this image. There's a lot of the country where you may not think of, major storms and things like that, but there's still plenty of lightning that goes on. If we think we've had lightning involved in our incident, there's a number of services that we can use that can give us lightning strike reports. A lot of these get their data from Vaisala's National Lightning Detection Network. There are other services that use that same data. This one in particular that I'm going to reference is one that used to be owned by Vaisala. It's now run by Corrugated. It's called StrikeNet. It's the one that I use most often. For about $100, they give you a nice map of your address and the surrounding area, and they'll put some dots on there showing you where any lightning would have struck. They give you a little more information to tell you how confident they are in that result. And then they give you a tabulated result that tells you usually coordinates of that strike, the time, and the amount of energy that they recorded on their sensor, basically how big that strike was. It's a pretty useful tool if you think you've had lightning, certainly something worth considering. At some point, you're going to have to go searching for holes. So depending on how big your system is in the building, that can be a fairly simple or a fairly arduous task. It's really depends how much tubing you have to look at and how much structure you have left. There are a number of different tests that we can run to figure out if we had a leak, where the leak is, and how big that leak is. So we'll take a look at each of these. There's a clock test, pressure drop test, soap bubble test, and a gas detector survey. First one's a clock test. Pretty straightforward, doesn't really require a lot of fancy equipment. Typically, we're going to use the structure's gas meter, assuming it's working and still intact, and some sort of stopwatch. We're going to turn off all the appliances and close or plug any openings that we're not concerned about, and then turn the gas on, take an initial meter reading, wait for a period of time, take a final meter reading, and the difference between those two readings and the elapsed time can be used to figure out what our volumetric flow rate is. And that's a very useful result for us because now I know how big my leak is. And I can use that to feed into calculations for filling times, if I've had an explosion, or fire models to figure out what my initial fire size was, and things like that. So that can be a very useful number to have. Pressure drop test is even more simple than that. Basically going to use a stopwatch and a pressure gauge. Again, turn off all your appliances, plug or close any openings you're not interested in. Apply pressure to the system briefly. Look at your pressure gauge, turn the gas supply back off, and watch your pressure gauge over time. If it holds steady, you can be pretty confident you've got a tight gas system that's not leaking. If that needle on that gauge starts to drop off, then you know you've got a leak somewhere. Unfortunately, this one doesn't tell you where the leak is or how big it is. So you still may need to do some flow testing separately if you needed that number to quantify that for other purposes. About the most simple test you can do, which is one that I like, I do it a lot, is a soap bubble test, where you take a soap solution and apply it to all potential leak sources. So maybe using a spray bottle or a paintbrush and some soapy water, you can go around to all the joints and fittings and apply some of that solution to those areas. And if you've got a leak, it'll start to blow bubbles in the soap, and you'll see those bubbles form and start to grow, indicating that you've got a leak at that point. Very cheap, very easy to do in the field. There are commercial products that you can use to conduct that test, or you can use just about any other kind of soap as long as it's not reactive or corrosive to the tubing material itself. You obviously don't want to cause any further damage to the system components. So as long as you've kept that in mind, just about anything will work. Gas detector survey. This is one that I don't typically do, and sometimes I'm not a huge fan of it, depending on how it's done and what's used. The instruments that we see on the left and the right of the screen are combustible gas indicators, and those make me a little bit concerned. They're generally not very accurate at detecting combustible gases, and they probably are not routinely calibrated. These are things that you may see an HVAC technician using if he's looking for leaks, or maybe a plumber, but they're not typically something that I would want to use for that type of test. In the middle is probably what you're going to see the guy from the gas company carrying. That's a little more representative of what they may use. They're going to have it calibrated for their specific gas, propane or natural gas. They're going to calibrate it often, and they're going to be properly trained on its use. So not uncommon to see them out there with one of these poking around looking for leaks. These guys, the combustible gas indicators, again, not really my favorite tool. And essentially what you're doing with this test is you take something that can detect the gas and you're sniffing around leak sources, trying to see if you've got that gas leaking out. A few tips for leak testing. Generally, you want to conduct your leak testing at system pressure. So if it's a half PSI of propane, you probably want to try and do it at a half PSI. If it's a quarter PSI of natural gas, then you want to be at that quarter PSI range. If you're unable to do that, typically you'd want to limit it to about 5 PSI as your maximum, because that's typically the max rating of the CSST system itself. There are some that go higher, but generally 5 PSI is where those things cut off. I already kind of mentioned this, but you want to use materials that are non-corrosive and are not going to damage the tubing or the fitting materials themselves. Obviously, we don't want to cause any more damage than what's already been done during the incident. One that may be useful in locating your holes, if you've got a lot of tubing in a house that's burned to the ground and you're trying to locate some small holes, maybe a millimeter or so in diameter, that can be a bit tough to do with air or gas. If you introduce water into the system, it may be a lot easier to find water leaking out than it is to find a small amount of air or gas leaking out. Again, you'd want to be careful with how you do that as far as pressures go. You obviously wouldn't want to apply, again, more than the system pressure or more than the maximum pressure rating of the system. If you've got other holes along the way, you may identify some holes that were formed during collapse, or maybe a portion of the system has been broken or torn, and you need to seal that up to look for other holes or other areas of damage. That can be done. Smaller holes can be sealed with Teflon tape, and then put a layer of electrical tape over it to kind of wrap that tight. You can also use duct tape. You can use hose clamps and things like that to apply some pressure to it. You can use modeler's clay, duct seal. We're not dealing with a lot of pressure in these systems, so it doesn't take a lot to seal it back up to the point where you can look for other systems, or other leak sources in other areas of the piping. Whatever materials you may use, keep in mind what you're doing may have an effect on some of your test results later on. Specifically, if you're going to do any analysis later on with an EDS to determine what elements are present in that material, you certainly don't want to introduce any new materials or new elements into that, or at least have a good understanding of what you did introduce, so your test results later on aren't skewed. Once you've identified some holes, now it's up to the investigator to determine what caused that damage. Is it mechanical? Is it lightning damage? Is it electrical damage that happened as the fire ensued? Or is it something else? And if we start looking at some of these, there are some things that we look at that can give us some clues as to what's going on there. This one, obviously, of course, that's not CSST, that's a flexible appliance connector, but we can see that, we've got an electrical connection missing its cap, and it's probably got arc damage. We've got arc damage on the connector there as well. This one looks pretty characteristic of electrical damage. I'd have to do a little more to figure out what caused it. But I'm going to start looking at things like the edges of the hole, and are they, can I see that they're fractured or broken? Can I see that they're torn? Maybe there's a gouge leading up, several corrugations leading up to a hole where it dragged across a nail or dragged across a piece of metal as the building collapsed or something like that. Some of these larger ones, I might start thinking electrical damage from the electrical system, where I've got a little bit more fault current capacity and expect to see some larger areas of damage. I kind of mentioned a few times already, paying attention to the areas where the CSST is run along with other utilities, other conductive objects. This photograph here on the left is above a furnace. We had some ductwork coming out of the furnace. It extended along. The CSST was run along the side of that. This is the black jacketed CSST with the double layers with the aluminum mesh in it. And right here in this area, we've got a couple holes in the CSST. We had a couple mating holes in the piece of ductwork as well. So that's an area that I want to focus on when I'm looking for that damage. This one here on the right, I've got a piece of CSST that was looped underneath a steel I-beam in a basement. And, we had them in close proximity. We have some lightning damage there. We have an arc hole in our CSST. And it eventually gets the jacket material going and then spreads to some materials above it in the structure. When I'm looking at arc holes, if I've already differentiated them from mechanical damage, there are some things that I can do to figure out, was that arc caused by the electrical system or was it caused by lightning damage? And I may need to start employing some fancier tools, some fancier techniques than what I can do in the field. So this is probably coming back to the laboratory for some more detailed analysis, some high-level microscopy. I'm going to put it under a fancy microscope and get a very good look at the surfaces around the periphery of the hole, looking for indicators of what may have caused that type of damage. And then from there, I may need to use a scanning electron microscope or an SEM to, again, get high magnification images of that hole and the surfaces around it, as well as conduct an elemental analysis with an EDS, which is usually coupled with the SEM. And that's going to tell me what elements are in that metal. So if I'm talking about stainless steel, I should be expecting things like iron and chromium and nickel, which are typical constituents of stainless steel. If I start seeing copper and aluminum that I see down here on the left of that chromatogram, that may give me some clues that, well, I've got copper, maybe it arced to a copper wire. I've got aluminum, it arced to something else. So that may give me some insight into what the scenario was that led up to that damage on the tube. Another fancy tool that we can use is computed tomography or CT scanning. This is one that's new to my laboratory, but we've been doing it for a while and pretty happy with the results. We can use this to non-destructively examine the tube. So we can take a piece of tube, put it in there, CT scan it, and get a look at the inside and outside surfaces. So that may be useful. I can see the outside surface pretty easily, but the inside surface I can't without cutting open the tubing and sectioning it. So I can do that now with my CT scanner, and maybe I'm looking for some metal spatter on the inside, and that may actually guide me. Eventually, I'm probably still going to cut this thing open, but that may guide me in where I make my cuts, so I know that I'm not cutting into the areas that have spatter on them. I can also do some sectioning to get an idea of the cross-sectional area of the hole, how big that hole is, and help me quantify the size of it. Again, I may need that later on for future testing or to determine flow rates for modeling or something like that. So let's take a look at some remedies. If you've got CSST in your house, some things that you can do to make it a little bit safer. This is kind of my list, and I've got them listed as a hierarchy of how I like to see them go. So the first one I've got here, to prevent CSST-related fires, don't have CSST in your house. If it's not there, it can't cause a problem for you. And that's certainly a rule that I like to live by. I don't have it in my house. It's a risk that I just don't want to have to deal with. If you do have it, it's not the end of the world. There are things that you can do. And probably the next best thing is install lightning protection system. Unfortunately, that's not something I see done that often in residential construction, but the option is there. We'll talk a little bit more about what that is and what it looks like. Then the next two I have both listed as number 3. It's because I kind of put them on the same level as far as effectiveness goes. If you've got yellow CSST, direct bond it to the grounding system. That's a must. Or if you have a choice of which type to use the arc resistant, the black jacketed CSST, because that is going to perform better under those lightning conditions. So we'll talk about each of these. This is a statement that comes off of a website, csstsafety.org. And essentially they're saying areas with high lightning activity should always consider installation of a lightning protection system. And that's great. And then they go on to list 23 out of our 50 states. So basically they're saying half of the country, you should be considering installing a lightning protection system on your house. Again, I don't think it's that common in residential construction. We certainly see, lightning protection systems on barns and churches and commercial buildings and things like that. It just doesn't seem to pop up as often, at least in my experience with residential construction. So when I say a lightning protection system, it's more than just putting a lightning rod on top of your house. It's a fairly involved system that's been designed and constructed and installed in accordance with NFPA 780 as far as meeting those requirements. When I look at what that system entails and what's involved in that, there are a few things. So here's a typical drawing from a lightning protection system vendor. And first thing I'm going to see down here is an indicator that that system has been designed in accordance with NFPA 780 and has been certified as meeting those requirements. So that's something I'd want to look for that's had some sort of design work and independent certification done. Then the system components, they're all pretty straightforward. We're going to have air terminals, lightning rods essentially, and they're going to be on things like chimneys and high peaks on the roof, along the roof ridge. Any metal penetrations or vents are probably going to get air terminals. And they're all going to be connected together with a very specific type of cabling, which is going to run typically along those roof ridges and then down and ultimately funnel that energy to ground through a grounding electrode. The cable is typically a loosely braided, large diameter copper or aluminum cable that's sized to handle a lightning strike and is braided loosely like that to dissipate the heat that's generated as it's carrying the fault current to ground or the lightning current to ground. And then we're going to have some sort of grounding electrode or grounding terminal that's going to funnel that right into the earth, into the soil. And you may have some other system components, surge arresters. You may have connections to water pipes. There may be a few other bits and pieces here or there. But those are kind of the basic critical parts to it. And here are a few examples of what that may look like in residential construction. So here on the right, we can see an air terminal up on this peak of the roof on a gable end. Here on the top left, we can see another air terminal. We can actually see the wire running along the ridge of that roof peak. And down here on the bottom left, we can see two metal vents, and each of those has an air terminal on it. And again, we can see the wire running along connecting those. And eventually those wires would all come together and go down to the grounding electrode to funnel all that energy back to the earth. The other thing I mentioned was direct bonding and grounding. Codes and manufacturer's instructions now have requirements for direct bonding CSST systems to the structure's electrical grounding system. So that was not always the case. That's something that's come out a little bit later. But it is something that's pretty uniformly recognized by the manufacturers and the codes as being necessary. And what we're talking about is really something like what we see in these photos. So a few different applications here. The center photo, we're right at the gas meter, and right where they transition from the gas meter to CSST, we've got a clamp clamping onto the CSST fitting and a fairly large wire coming off of that. On the left, we've got one. We're coming into the structure with some steel pipe fittings, and they've clamped onto one of the steel pipe fittings. And again, a fairly large copper conductor on there that's going to run back to our grounding system. This is an image on the right from the manufacturer, kind of telling you how that should be done. So you would typically connect to the pipe, the fitting, but not the tube. We obviously don't want to put that clamp on the tube because it's going to crimp down on it. It's going to cause some damage. But we're dealing with a clamp right on the fitting or on a pipe and a large gauge conductor. A bunch of studies out there have shown that this improves the situation with CSST, especially when we're dealing with our yellow jacketed CSST products. It's going to allow them to funnel some of that lightning energy back to ground more effectively and prevent damage in some cases. However, it hasn't shown to be completely effective. There's still been studies that have shown that you can have lightning strikes that still perforate the gas pipe and still cause other problems, same as if you didn't have it bonded. So it's not 100% effective, but it's certainly an improvement. So when we talk about bonding and grounding, let's kind of define those terms a little bit, just so we understand what we're talking about. These are terms that come out of the National Electrical Code. And again, we're mainly talking about plumbing products here, so the two don't always go hand in hand, but that is where these terms come from. Bonding is effectively connecting things together. So we've got a bunch of metal parts, and we want them all electrically connected together to be at the same potential or same electrical voltage if one exists. So that's the bonding process. Grounding is literally connecting all that stuff back to the earth, back to the soil. And that's done through a connection to a ground rod or a grounding electrode. What that electrode is varies depending on local conditions and codes. But generally, it's going to be some sort of electrode system where your electrical system is already tied. Around 2006, most of the CSST manufacturers started requiring direct bonding of their CSST products with a dedicated bonding wire back to the electrical system. So that was already in their instructions in the design and installation guide. Prior to 2009, the code required metallic pipings, gas piping systems to be bonded to the electrical grounding system, but it didn't really give any detail on how that was done. And the other issue was it gave an allowance for connection to a grounded appliance to serve that purpose. So if I had CSST running to a furnace and the furnace had an electrical connection for the blower fans and the electronics, the electrical connection is going to have a ground wire coming in with it. That was acceptable prior to 2009. The problem is that ground wire is designed and sized for personnel protection for shock, primarily, as well as for proper operation of circuit breakers and fuses. It's not really designed and sized to handle lightning current or funneling lightning currents back to the earth. So it wasn't really effective in doing that. And eventually the code started to recognize that. And after 2009, the National Fuel Gas Code was revised to have more specific requirements. So from 2009 forward, what we have in the National Fuel Gas Code now is this nice picture that shows you how it's done. There's actually, I think, several pictures and some specifics on what you need to do. It's got to be a 6-gauge or larger conductor. That's typically what I see is like a number 6 solid bare copper or aluminum equivalent. Connection to a metal pipe or CSST fitting with a listed clamp. So you can't just use a hose clamp or something. It's got to be a specifically listed grounding clamp. And a maximum conductor length of 75 feet to get from that connection to the CSST back to the grounding electrode for the system. So that now exists in the National Fuel Gas Code with a bit more detail than what we've had prior to that. So one issue that comes up is the difference between trades. If I'm having gas pipe, okay, so if you're having a gas system installed in your building, the guy that's going to do that work for you is this guy here on the left. That's our plumber. And his book is the National Fuel Gas Code. That's going to have all of his requirements on how he's going to install his plumbing. It's also the one that has the requirements on how to ground and bond the CSST system. It's going to have the requirements for the 6-gauge wire, 75-foot length, listed fitting. So that all exists in the Fuel Gas Code. The issue that we have is the guy that might be doing the wiring is this guy over here. That's our electrician, and his book is the National Electrical Code. And all that says about gas piping is it needs to be bonded and give some general requirements, but it doesn't give the specific details of how. So there's a little bit of a disconnect in the trades in who's responsible for what and where the requirements lie. Unfortunately, the grounding requirements, which usually fall under the electrical code, in this case fall under the fuel gas code. So if your trades aren't talking to each other well or aren't working together well, or maybe they're not even at the site at the same time, that leaves the chance that something might get missed or something might not get installed properly in that bonding system. And that can certainly cause some issues. So I talked a little bit already about arc-resistant CSST or lightning-resistant CSST. This is the manufacturer's response to some of the concerns over the product. So again, over here on the left, we have our legacy product, our yellow-jacketed CSST, where the jacket really served not many purposes other than to smooth it out. Now we've got over here on the right a couple of black-jacketed products. And what they've done is they've realized that, okay, we don't want to perforate that inner tube. So if we can spread out the lightning energy over the surface of the whole product, it'll have a better chance of surviving. So on the inside, these things are basically the same. It's still that thin wall corrugated stainless steel tube, but now we've got this conductive or semiconductive jacket on the outside, which coincidentally may have something to do with why it's black versus yellow. If we're trying to make plastics conductive or semiconductive, adding carbon is a common way to do that, which may have affected our color. But now, so we've got this jacket, which, at least for the purposes of lightning, is conductive. It's not a great conductor, but it is conductive to a certain extent, and that can help dissipate the lightning energy over the entire surface of that tubing versus allowing it to be focused and pinpoint in one particular location, which is what's causing the damage and the melting of the stainless steel tube and forming that hole. So one manufacturer took this approach where they have one layer of conductive black jacketing. This is another manufacturer that took a different approach, and they've got 2 layers, one conductive, one non-conductive. And sandwiched in between, they've got this aluminum mesh, which again provides now more mass, more metal, more material to help spread out and dissipate that lightning energy and provide protection for the pipe on the inside or the tube on the inside. So these are three basic designs that we tend to see that are out there on the market. Around 2005, we start to see the first black jacketed products coming out. By 2011, Omega Flex, who's one of the larger manufacturers and produces a lot of CSST, moved away from their yellow product. They abandoned that and are entirely with the black product now. Their Counter-Strike product is the only one that they sell. There's still several manufacturers out there that produce both. Tight Flex produces the yellow gas tight, and they also produce Flash Shield, the multi-layer product as well. There are some that only produce yellow. I think Home Flex only produces the yellow product. I think there are others that only produce a yellow product. It's just based on what the manufacturer thinks they can sell. But there are definitely still a lot of yellow CSST products out there on the market. Certainly, a number of them that you can get very readily available and very easily. So let's talk a little bit about some of the legal aspects of CSST and some things that have gone on. And probably the right place to start is with a case out of Lubbock, Texas. I'm going to call this the Brennan Teal case. And this involves, it was back in August 2012, involves a man named Brennan Teal who was visiting some friends in Lubbock. A storm rolled through, there was some lightning, and they had a lightning strike at the house. And pretty quickly, these guys realized that something's not right, and they go on to investigate to figure out what's going on. They're smelling some smoke, and they're trying to find the source. And as they're poking around the house, trying to figure out where it's coming from and what's going on, they realize they've got some smoke up in the attic above the garage. And there's a access way through the garage to get into the attic. And Mr. Teal goes up there to make access to the attic. And as he does, there's some sort of backdraft event, which ignites all the fuel gases that were up there and all the smoke that's up there. And he unfortunately takes the brunt of that and ultimately dies in the incident. Following that, the fire marshals come out, conduct their investigation, and they determine that there was a lightning strike, there was damage to the CSST, and that was the cause of the fire. In response, in 2012, so later that same year, the city of Lubbock issues a moratorium against using yellow CSST in their jurisdiction, so no more yellow CSST. 2013, they go a step further and say, you know what, we don't like the CSST at all. We don't want it at all in new construction. So they completely ban it for a period of time. By 2016, we start seeing those black jacketed products, and there's a number of them out there. We've got the single layer and then the multi-layer. They look at it and they see that multi-layer product as being more robust. It's designed to a different standard. It's ICC LC 1027, which has a lot higher lightning resistance test. It's a higher energy discharge test. And they lift their ban and say, okay, you can start using CSST as long as it's this multi-layer black jacketed stuff that passes this higher energy lightning test. So as of 2016, that's what they're allowing. And that goes on for a while. But in the process, Omega Flex, who wasn't actually involved originally in this case, gets wind of it and says, hold on a minute, that doesn't seem right. This test maybe has some issues. This product is maybe not the best product to be using. So they file a lawsuit against the city of Lubbock to stop the introduction of that LC 1027 standard and the higher energy test for multi-layered CSST. And that went around for a little while in the courts. Last year in 2019 was another recent development in this one. And it actually wasn't related to this case, but the state came out and changed the law that was allowing the local jurisdictions to further restrict some of these products and installations. So the state basically came back and said, if a product is allowed or is permissible under a nationally recognized code, the local jurisdictions can't prohibit it. So that basically prevents Lubbock from having that ordinance on the books. So Lubbock has had to remove that ordinance. And as a result, when that went away, Omega Flex dismissed their lawsuit So we're still kind of waiting to see how all that one shakes out. I'm sure we're not done down there in Lubbock. That's certainly one worth monitoring as time goes on. Also, what came out of that has been a bunch of squabbling amongst the manufacturers and others involved in CSST. There have been claims of patent monopolies, patent infringement, bias. Omega Flex claims that TightFlex has a patent monopoly because they have a patent on that multi-layer CSST product. There's a private engineer out of Texas that claims that TightFlex with that multi-layer product is infringing on some of his patents. Omega Flex is claiming that the testing that was performed to support the Lubbock ordinances is biased in favor of people with other interests in it. So maybe those tests were not valid or were not something that would be reliable. They've also claimed that the standard, the ICC LC 1027, is biased toward that multi-layer TightFlex product. So there's a lot of things going on there and a lot of moving parts, but certainly it's worth keeping an eye on from a CSST standpoint to see where all this litigation goes. And new things do come out periodically. There have been a number of class action lawsuits around the country. This is one, it's a little bit older, out of Clark County, Arkansas, and the settlement was somewhat relevant. So in this one, it was a class action of a number of people that had CSST in their homes, and you can see they filed suit against a number of different manufacturers. It wasn't limited to just one particular one. It's a variety of them that existed at the time, and the court found for the plaintiffs, and they awarded, as part of the settlement, reimbursement of direct grounding and bonding of existing systems. So if you have this stuff in your house in Arkansas, you can use this to get coverage for having somebody come out and do the direct bonding and grounding if that wasn't done originally. It also covers the cost of the installation of a NFPA 780 lightning protection system. So those are pretty relevant things that if you've got this stuff in your homes, you may want to consider. And certainly other states have awarded similar things in other cases. I know there's one here out of Maryland with a similar finding. They didn't award the full reimbursement, but it was a partial reimbursement, basically the same thing, coverage for direct bonding and grounding, I think an inspection of the system, or a portion of a lightning protection system. So things that could be pretty important to people that have this stuff in their houses and they're affected by this. Of course, the courts have gone both ways on the topic. The plaintiffs have won some and the manufacturers have won others. It really depends on the court and where we are and what the issues at hand are. But certainly it's not completely a one-sided argument. The courts have seen both sides of it and have found in different cases, different ways. One last court case that has some relevance here is Tincture v. Omega Flex. This is out of Pennsylvania. And this one actually has not only an effect on CSST, but a lot of product liability cases where it went to the state Supreme Court and they really ended up redefining how you determine a product to be defective or unreasonably dangerous. And it gave that decision-making authority back to the jury as opposed to how it had been done in the past. So again, something that's still probably going on in the courts, and I would expect to see more on this case come out in the future, but again, pretty relevant to what's going on here. I've listed here a handful of CSST resources. There's certainly many more out there. These are just a handful that I use. Worth taking a look at, seeing what's out there. I'll give you a little bit of word of caution. These are things on the internet, and beware what you read. Some of these are independent sites that have one goal in mind, and some of them are manufacturers' sites that have a different goal in mind. So watch out for that. Good to read them all and see what's out there, but definitely consider the source and weigh it accordingly. I've also listed a handful of papers here. These are some of the good ones that I've referenced in the past. Again, if you Google CSST and lightning or anything along those lines, you will get a very long list of things that you can make reference to and then that you can read on this topic. There's a lot of information out there. I'd encourage everybody to take a look at all of it and see what's there and form your own conclusions and decisions. But definitely there's a lot of good information to be had. Kind of wrap it up with a quick summary, the things that we talked about. We looked at some of the basics of CSST, where it came from, its history, how we install it, Looked at some failure modes and how we examine CSST, the different types of damage. Talked about some remedies that we may apply for existing CSST systems that may be in people's homes. Talked about some of the new products, the arc resistant stuff. Looked at some of the legal aspects of it. That's pretty much what I've got. So I'm going to wrap it up there. I believe we're going to have a question and answer session at some point where you can submit questions and we'll address those at a later date. But that's basically what I've got. I'm going to turn it back over to you, Bill.
Great, Jeremy. That was amazing. I mean, it was packed full of information. And we really, really appreciate your time. Like Jeremy mentioned, Jeremy's going to give us 10 questions, either multiple choice questions that we'll make available to you to take to get a tested certificate from our organization for attending this training, as well as taking the test. So we'll come back and have Jeremy back to answer questions live. We'll get it posted, and we appreciate your time and hanging out with us today.
No problem. Thanks a lot.
Thank you, Jeremy.